All right, I start the proceedings. I'm Santa Claus. This is the last quantum seminar before Christmas, so the Christmas version of the quantum seminar. We are super happy to have Irina Novikova, and because Dima insisted so much, she can introduce her.
Yes, I just want to say that I met Irina when I think she was like second year PhD student, maybe third year PhD student.
First year
PhD student, and that was we're gonna skip this number how many years ago, but I just want to say that from that time, so we met, and I invited Irina to come to our Berkeley lab, and I think that was Irina's potentially first visit to another lab, but that was actually a start of a lifelong collaboration, and Irina has been sort of one of my closest collaborators and friends for many years, and I think that for the first 5 years of our acquaintance, maybe I had a thing or two to teach Irina, but ever since then I was learning from I have been learning from her, and now she's a professor at College of William and Mary, and maybe not many people recognize this, but that was the first fact that was instilled upon me when I visited there, that this is actually one of the Ivy League universities in the,
No,
yeah.
We're not Ivy League. We're second oldest in US, but we are not Ivy League.
No?
No.
See,
we're better.
I thought you, okay, then I'm okay, anyway. But very old university in the United States, and a very nice one. And so now I should shut up and let Irina tell us about exciting science.
Yeah, just to add, yeah, so William and Mary is the second oldest university in US. The fact which our faculty like to brag about, that Thomas Jefferson went there. The fact we don't like to mention is that he didn't like his experience, and after that he decided to found a different university in Virginia. But yeah, so some of the first presidents of United States went there, and it is a nice place. So if you are in US, I highly recommend visiting Williamsburg. College is beautiful, but the city itself is beautiful as well. However, I will be talking about slightly more modern version of what's going on here. So first of all, thank you so much for inviting me. Again, I would love to some point to visit in person. That has been my dream for a long time, since basically Dima moved to Mainz. But I'm very happy to at least been able to tell you what we are doing here in this environment. So today I will be talking about the methods we're developing for low light applications. So the idea is that if we have something which shouldn't be exposed to light, how we can still see what is going on. So of course, any work like this will not be a work of individual persons. So this is actually a collaborative effort between our experimental team, which includes another professor, Evgeny Mikhailov, who is also actually my husband, and also a long-time admirer of Dima. And our graduate students, one of them is left already, and the other two are still in the program. And we have a theory support from the quantum group at Louisiana State University. It was led until recently by John Dowling, who unfortunately passed in summer 2020. It's a huge loss for us, but nevertheless, we still continue working, and we have kind of people who continue his legacy there. All right, anyway, so what is the kind of main motivation of what we are doing? It's how we see. I think everybody here knows that the way we see is we have light, which can be abstracted by the object, and then we use the light detectors like our eyes or a camera to figure out what is the shape of the object. And I think everybody from everyday life know that the brighter is the light, the easier it is to see what is the object. So for example, here we use the very simple kind of knife edge, we put in a laser beam, and of course you can very easily detect the shape of it. However, where the problems start, if you don't want to have your light to be very bright, and in this case, if you start dropping the amount of photons which are in your light beam, then the other problems will wake up. In particularly, no light source has every light source has its own internal noise. So for example, camera will have some dark electronic noise. You also may have some stray photons from the background illumination and some other stuff. So if you have a very few photons, you can barely distinguish the object. So you can see the bottom on the bottom here, this is the same knife edge. And I think if you squint really hard and you have a good imagination, you can kind of see the images here. So this is where the black is, but it's extremely hard to resolve it. So what we propose as solution is we use the quantum noise imaging to avoid this problem. So now when I told you the solution, let me go back and tell you what actually is going on. So this is going to be kind of an outline of my talk. The one, what do we mean by quantum noise? Second, how we measure this quantum noise, how we image quantum noise, and then can we image quantum noise of kind of non-quantum state? And finally, can we image the quantum noise without using the camera? So sorry if that's kind of an elementary introduction, but just to make sure that we are on the same page. And also it is quite early here, so maybe it's to keep me in the loop. So when we are talking about quantum noise, we specifically means the fluctuations of electromagnetic field, which are connected to the photon statistics of the light. So if we're thinking about the laser field, then of course it is a coherent state. And that means that this electromagnetic field can be represented as the combination of the two quadratures, which are by itself a combination of creation and annihilation operators. And then, of course, these two quadratures do not commute with each other, which means that we cannot measure whatever electric field is precisely. And if we kind of visualize it, that means that our sinusoid would represent the kind of time and space dimensions of electromagnetic field will be fuzzy. And this fuzz is exactly because of this non-commuting properties. And that's what we call the kind of a short noise. We can also often visualize this quantum field by its mean amplitude and also the noise ball. So basically, what is the uncertainty for the position of this electromagnetic field vector within this with this mean position? In reality, of course, for any like a normal laser field, this noise ball is very small because it's actually the size of the noise ball stays the same independently of how strong the coherent field is. So that's why if we have a lot of photons, this noise ball is so small that we don't even have to worry about it, which is kind of a good news because that's why we can use the classical description.
It's not, sorry, it's not, you just said it's not small, the same size, but it's relatively small.
Relatively small, yes, relatively small. Sorry. So, so that's why we, for most of the application, we don't have to worry about it because if you have, let's say, 10 to the 12 photons, and the size of the ball will be proportional to square root of that, and then the effect is like very, very small. The one thing to keep in mind, because it will be important.
Sorry, I think I disagree with this again. Because I think the size is 1, and what is square root is, I think.
Oops. Okay, let me see.
When you take intensity.
Yes, Dima, you're absolutely right. Yes, I skip it here. So if I use this field for the measurement, then the intensity of the light will be proportional to the average number of photons. The fluctuations of intensity would be proportional to the square root. And something which I will use in the future is kind of the normalized variance of the noise, which is noise power of the fluctuations normalized to the average number. That's going to be 1 for the coherent state. Very, very good. Thank you. Also, just to keep in mind is that for quantum treatment of electromagnetic field, we have vacuum is also have fluctuations, so it will have the same size 1 noise ball here. So when we measure nothing, we will still expect some sort of noise. Okay. All right. So because coherent state is kind of our baseline. To do something interesting, we need to do something interesting with the coherent state. So in particular, today, I will be talking about a squeezed light quite a bit. So I'm in general, if I look at a theorist approach, is how we make a squeeze light. We take a coherent state and we squeeze it with a squeezing operator. So what happens in this case is the round ball gets squeezed in one of the directions. So for example, here we have a phase squeeze light because the amplitude is kind of have more uncertainty now, and the phase, the orthogonal quadrature, has less uncertainty. And of course, then if we kind of plot the electromagnetic field, we can see that it's not a it's not kind of uniformly fuzzy. It's fuzzes more on the antinodes, and you can determine the nodes quite nicely. In the talk, really, I will be paying much more attention to the squeezed vacuum. So we're doing the same thing. We're taking coherent vacuum and we're squeezing it. And in this case, we create this interesting state. It has a zero average amplitude quadratures. But if we measure the noise, it will actually be phase dependence, because depending on which of the quadratures we measure, you can have more noise or less noise compared to the regular coherent vacuum. Now, I won't talk too much about it, but another quantum source which we are studying is a two-mode squeezing. In this case, we take two modes of a light, and then we start adding or subtracting the photons to them, kind of like a pair generation. In this case, each of the fields itself will be actually noisier than a coherent state. It will be in a thermal state, something which we will use later. However, together they will be squeezed. So their relative joint quadratures will be squeezed. And people have used this for actually for imaging purposes as well, although that's kind of outside of what I will be talking today. Just very briefly, how we make our squeezed light. Again, Dima mentioned that we do have a long history together, and this source was actually one of the brainchilds of this collaboration. I think probably Dima was the first who recognized what is happening, but we can generate squeezing using the atomic vapor. If we send a linearly polarized light to the system, which internally have this self-rotation. So, okay, I tried not to, to put too much in it. So essentially, if you have a material in which the linearly polarized light, elliptically polarized light rotates by a certain amount, then if we send the linearly polarized light, there is no actual rotation. However, there will be the cross-phase modulation between the two circular components. And what it will look like on kind of the outside is that the vacuum, coherent vacuum, which was in the orthogonal polarization, will actually be squeezed. And we can also position it as the kind of polarization squeezing. So we take a regular light on the Jones sphere, and this action will squeeze it, and we can control which quadrature the squeezing will be measured in. And this work experimentally. Again, this is one of our work, but there has been many demonstrations for the squeezing before. I think we can get up to like 2 or 3 dB of squeezing at rubidium transitions, and there were multiple applications, but here we just use it as a source of squeezed vacuum.
What
and again,
would it be limited by?
Huh?
I mean, what would that particularly system limited by? Is it just because there's so many optical surfaces, or?
It is okay. Well, okay, maybe it is. So we don't 100% sure what limits that. So we know one thing is that this is a multi-mode process, spatially multi-mode process. So as we increase the density of atoms, so we increase the strength of this interaction, the squeezing start occurring in a different spatial modes. And unfortunately, this squeezing is not kind of compatible with each other. So these modes basically start to, at detection stage, they start destructively interfere. So at the end, we actually get less and less squeezing up to a certain after the certain atomic densities. However, if I'm completely honest, we're still trying to figure out. Actually, the whole motivation for this work originally was to try to understand why we cannot get more than like 3 dB of squeezing. And it's not only we, but like everybody who tried.
Because like with photons, I think they get 15 dB or something like this, right? I mean.
So yes, at 10. 1 micron essentially. So interestingly enough, at 800, I think the best squeezing people have gotten in like a degenerate squeezing, so not a 2-mode squeezing, it's actually on the order of 3-4 dB, even with crystals and other methods. So we do have a hope, because with actually, if I go here with the non-degenerate, the 2-mode squeezing, where we use a similar system, but we rely on 4-wave mixing gain. And then we look at this 2-mode squeezing between the two optical fields. People have been able to get up to like 10 dB of squeeze or 9 dB of squeezing. And even for our experiments, so basically using similar lasers, similar cells, everything else the same, we can get 5-6 dB. And we know we don't have that we have less power than they do. So there is something about the quadrature squeezing, which is make it harder, and we believe that it's a spatial information. And again, we're still working on it, but not quite cracked it. So in a sense, you can say that we got sidetracked by this interesting imaging applications. Yeah, so I'm pretty much said what's going on here. So this is just another version of atom-based squeezing, different types of squeezing, 2-mode intensity squeezing. And in this case, the useful signal when we looked between the intensity correlations of signal and conjugate field. And as I mentioned, we can get quite a nice reduction of the mutual intensity noise between the two. Okay, so now when I kind of introduced what quantum noise is fundamentally, how we measure it. So typically, we don't use just a photodetector to send a squeeze light in and see what is going on. Typically, we use the balanced homodyne detector to diagnose our state. How it works is that we take our quantum light, and here I will be talking right now mostly about squeeze light, but in principle it can be any quantum field. So we send a weak field and we mix it with a strong local oscillator. Local oscillator is a strong coherent field. So as I said, in this case, the quantum fluctuations are kind of negligible. So we will treat it as just a strong coherent field. Classical field. And then we mix them on 50-50 beam splitter. And in this case, of course, the signals on the both channels are going to be a combination of the two. And then we subtract the signals and look at the photocurrent on this balance detector. If we balance detector really well, then kind of the large offset because of the classical field is going to disappear. And the remaining term will contain information about both quadratures of my quantum fields. And it will be multiplied by the amplitude of my local oscillator. So essentially what this method does, it's first of all allows you to pick which quadrature you want to measure, because that will depend on the phase of the local oscillator. And then of course you can amplify it so that you can detect it with like a regular photodiode. You don't need to worry about the dark noise anymore. And spoiler alert, this is basically going to be our secret sauce of how we do our imaging. But in terms of measurements, the way things are going to look like is like this. So the black line here is so short noise. So essentially, if we send, let's say, the regular vacuum in here, in this case, we measure the normalized noise, normalized quadrature. So if in logarithmic scale, it's going to be 0. And then if we start, if we send a squeeze light and we start varying the phase of the local oscillator, we can oscillate between squeezed and anti-squeezed quadrature. So we will have even less noise than the quantum, than the coherent state, or more noise than the coherent state. All right, so now we want to actually use this extra noise to extract some useful information, but we want to do it with the camera. And in this case, we want to use a similar trick as a balance detector, but now it should be applied to the camera. And we will be using in the talk kind of two approaches. And experimentally, we will use basically the camera realization, generalization of this effect when we take our squeezed light and we mix it with a local oscillator on a beam splitter, and we detect both of those beams and analyze them. However, we started with the idea of like discussing what happens if we have the squeezed vacuum and maybe we leak a little bit of the light field, maybe unintentionally, and we see what's going on with the image. And again, oops, sorry, my cat decided to contribute to the talk.
Actually, since your cat has interrupted this, may I ask you a quick question
Yeah,
about
absolutely.
this balance, this homodyne detector? So what is the decrossing angle that you choose again?
Which angle?
So on this, on the left, you have this polarizing beam splitter, right? So you have a so most of the local oscillator goes. It's not balanced, right? It goes.
It is balanced. So it's the detector is at 45 degrees with both of those polarizations.
I see.
So it's supposed, it's, you know, if everything's fine, it is balanced.
But it's not essential, right? Or is it? It is essential, I guess.
It is essential because, again, in ideal case, of course, the noise of the local oscillator will be small. In reality, we can have some technical noises in the local oscillator. If it balanced, we suppress them. If it's not balanced, then yeah, it gets in. So
okay.
Yep, absolutely. All right. So what it turns out is that we can actually use this kind of leakage with this mixture of the squeezed vacuum with a little bit of the classical field to diagnose the squeezed field. Because one of the things which was not at least obvious for us in the beginning is that if you start with a squeezed light and you leak a little bit of coherent field in, but let's say not many photons, so that you have much more photons in this coherent leakage than in your squeezed vacuum, you might expect that the squeezing disappears completely. And it was nice to see that actually it's not. The balance kind of changes. Your squeezing, it becomes smaller than your anti-squeezing, which is a little different from like a classical squeezed vacuum. But nevertheless, we still have sub-shot noise and above-shot noise variations. And actually, it is possible to kind of parameterize this feature using some of the parameters Q to kind of trace what is the amplitude below and what is the amplitude above. So now we can. It also means that we can maybe use it on a camera. Now, moving from camera to the photodiode has an interesting consequence, because what is camera? Camera is actually an array of many photodiodes. And now your light beam, when it hits the camera, it actually covers many of these little pixels. So that means that each pixel sees a very small portion of your optical field. So that means that each pixel essentially has a huge amount of loss compared to the original field. Now, in all the previous measurements, I basically didn't discuss at all any spatial distribution of the light. We use this approximation of single mode, everywhere field, and you detect all the optics. And in the photo detector, we can do that because we can make a large photo detector. However, in the camera case, we have to consider the fact these losses if we want to get the pixel information. And maybe that's the time I thought maybe good to just briefly introduce kind of the model which we use to describe these losses. It's called the beam splitter model. So if we have any quantum signal which we send in, and we want to take into account that it's only fraction of it can be detected, in this case, we model this process as a beam splitter, which says that only a small output, like proportional to the transmission, which is the loss coefficient, goes through. But of course, it's a quantum field. That means that on a beam splitter, it adds some of the vacuum field from the port. So that means that if we started with the squeezed vacuum field, and we have a large loss, the output will be significantly less squeezed because portion of its quadrature has been replaced by the coherent vacuum. So if you're thinking about, this squeezed quadrature, your ball suddenly becomes a little more round. So we have to take this into consideration, and that's why you will hear me talking about binning, which means that if you take one pixel, we will have to take into account that it's lossy. But if we combine the data from multiple pixels, we actually kind of regain regain the squeezing back. And again, our theories have confirmed that this is indeed the case, even though it's slightly different from just having the one large photodetector. But on the other hand, it gives an interesting opportunity to explore how the light is behaving, because now we can take an image, and we know that if we use, let's say, individual pixels, that corresponds to the very large amount of loss. So it's gives us the very low photon counts and very, very low variances correspondingly. However, as we start to bin, we can vary this amount of photons we take into account. And what is interesting is that because of this process, we actually can, we can take into account the fact that the camera may have other loss sources. So for example, all the cameras have residual reflections, or they may not have 100% quantum efficiency. But now it's because losses are kind of folded into our analysis, we just can't take them into account. So for example, here, if we have this squeezed light field and we send it into the camera, now we can kind of have a large, the whole dependence of average photon counts and the corresponding variances on the different amount of losses. And by using that, again, by using this one kind of parameters to describe these curves, we actually able to extract the average number of photons for the squeezed field. And from that, we can actually predict what kind of squeezing we can get. And this curve here is essentially, if we track the lowest amplitude we can get and the highest amplitude we can get, and they, depending on this angle, we should get the same value of these parameters when they feed them. And indeed, that actually works well. So we didn't have experimental verification for this work, but our Louisiana colleagues, they have run the numerical simulations, which kind of very realistically should represent the situation. And they have shown that indeed we can accurately detect the amount of squeezing in light just by imaging it on the camera. And the only thing we really need is to be able to vary the phase between the coherent field and the squeezed vacuum field, which is typically and not a very hard task experimentally. Okay. Now I'm getting to where what our work is actually really is. Okay, I think I'm okay on time. So what problem we're trying to solve here? We're trying to get the shape of an object. So at this moment, it's just opaque object. And we want to measure its transmission map. So essentially, how much transmission we get with some spatial information on it. So how we would do it traditionally is we take the probe field, we take a reference field which doesn't have the object, we divide by 2. 2 intensity maps, we get the transmission. And as I discussed earlier, is the issue is that if we have a perfect coherent light and a perfect camera, in this case, we actually have the signal to noise ratio, which we define by, how many counts we have on the unobstructed area and how much counts we have if we have a 100% absorption object, so basically vacuum. Then we will, we get the standard square root of n dependence on the signal to noise. However, if the camera have a dark noise, this signal to noise, of course, will not be so good. So this is just an example when we have a fairly weak coherent field, and we have this kind of knife edge inserted here. And of course, if we calculate the transmission map, it doesn't look good at all, mostly because we have a lot of fluctuations because of the dark noise. Of course, we can average and so on, but still, that's an issue. So basic idea of our methods is, instead of looking at the number of photons we send in, is to look at the quantum noise, to measure the quadrature noise of the light. As we discussed, when we have our kind of quantum noisy field, let's say the squeezed field for right now, it may have smaller or higher noise quadrature. However, if we have an opaque object, which will replace the squeezed noise with the coherent vacuum, which have obviously the shot noise. So that means by analyzing the changes of noise kind of spatially, we should be able to detect the object how it is. And because we can use now the homodyne detection, we can lift our signal above the shot noise, about the dark noise of the camera, and we basically protect ourselves from this technical noise, or maybe from background illumination, from anything else, because the actual reading of the camera will have a fairly large number of photons from the local oscillator. Okay, and this is, oops, sorry, wrong way. And in this case, the way we can calculate the transmission map is if we know this normalized variance for the kind of for our probe field that's with the object, and we also measure it without the object, and then we can calculate the signal to noise. And one thing is that if you look at the ratio of sensitivity, expected signal to noise with this quantum detection for squeeze light compared to like a classical description, it looks something like, oops, sorry. Something like this. So if we don't have a dark noise on the camera, then these two methods are basically equivalent. However, if we do have the dark noise on the camera, the quantum shadow imaging, that's how we call it, it actually gives a better signal to noise ratio if we have a small, if our photon numbers is essentially less than the dark noise of the camera. So this is how experiment is done. So essentially we create the squeezed light using the polarization self-rotation squeezing I mentioned above. Then we separate it into the two channels. One is a local oscillator. One type of our pump field will become a local oscillator. So we just attenuate it for the right amount for the camera. And then we have our vacuum light. So we can insert our object here. We recombine them again, rotate their polarization by 45 degrees. And basically this is our homodyne detection, divide it again, send it to camera, and record the images. When we got the two images together, essentially we record 4 images very close to each other, so we don't susceptible to like vibrations and turbulences, so on. Then we subtract the 2 images, they are very nicely balanced. We looked at the noise, and then we can calculate the normalized variance for each pixel. And if this normalized variance is 1, then essentially we have a shot noise, the classical field. If it's less than 1, we expect squeezing, or if it's more than 1, we expect anti-squeezing. Now, if we just do it pixel by pixel, we essentially are at the shot noise level, how you can see here. And this is because it has been shown that this field, the squeezing in this field has certain amount of certain mode structure. So in order to be able to detect the squeezing, you have to have a certain size of your detector to catch all the quantum fluctuations. Otherwise, that's like trying to detect the squeezing, very, very noisy detector. So that's why for most of the measurements, we go through binning, where we collect the light from the counts from several points, and then we kind of add them together and assign to the point again. So it's kind of makes it more make our effective detector size bigger. And that's what you see, what we have around is that if we start with basically like each pixel, the noise is basically the shot noise. But once we start binning them together, we can achieve, here we look mostly on the anti-squeezing just because our system has quite a bit of losses, but we can see that the variance grows according to expectations from the anti-squeezed field. Okay, so can we see something? Looks like yes. So for example, if we take a little cross or plus sign, there is still discussion what's the best way to call it, and we put it into the into our system. So we will have the squeezed vacuum with roughly with less than 1 photon per image in it, and then we send it to the camera. By using this binning, we can recreate the shape of this cross. So you can see it right here. Actually, what is quite exciting is that you can see that there is a little kind of side effects here. So it's actually even hard to see it on this image. We have to kind of highlight it like overexposed image. That's because the mask had multiple crosses printed. So even though this little crosses are kind of on the skirts of our laser beam, when we measure in this noise, because we still have the squeezing in this part, we are actually still able to kind of resolve the structure. So that was kind of exciting. Now, of course, we can characterize what's going on again, just using this knife edge again. This is the classical image just to show you that with the dark noise, which is comparable with the number of photons which we send, images don't look very good. Binning helps, but not a lot. And if we do the same thing with the squeezed vacuum now, there we can produce the maps of much higher qualities again, because with the homodyne detection, we essentially eliminate the effect of the dark noise of the camera. And how good it is, obviously, we have to do a binning here. And the binning, of course, reduces the resolution. So we have to do kind of a trade-off. If we want the higher signal to noise, we have to bin, but if you bin, we lose kind of resolution. And this is just a demonstration. The blue line, this is a similarity, like how well we can recreate our image using like a very bright light. So when the dark noise is not an issue at all. And you can see that as we start to bin, of course, the similarity goes down because, because of the resolution goes down. If we use the squeezed light, as you can see, we have to reach certain amount of binning to match the size of the squeeze light mode. But after that, we actually perform very comparable with the bright classical lights. And these two images is just if we use the classical images with a small number of photons, still much smaller than the average number of photons in the squeezed vacuum. And as you can imagine, for this image, we show them to show how terrible it is and how good is our squeezed vacuum light. So up to now, I talked about squeezing. And of course, squeezing is a really cool optical source. However, it's not easy to make one. It requires a lot of careful arrangements. And also, it's not available in many wavelengths. So for example, I think invisible light, invisible range, it's almost impossible to get squeezing. I actually don't know if the squeezers exist really. But if you look at our methods, it doesn't matter what exactly is noisy about the light, right? So we just need a light with the quadrature noise, extra quadrature noise. So the next question, which we ask our theorists, and is like, can we use the thermal light? Because if we use the thermal state, that makes this method much more universal, because there are many ways to create the thermal state. So for the next results, we were actually using two of them. One, we used one of the fields from our two-mode squeezer. Again, I'm not saying that this is necessarily the best the best source of the thermal light. But we had it available and we had it very nice characterized. So for conducting the very careful comparison with the theory, that was a great source to use. And also we know that this is a thermal light. But we also repeated these experiments using basically just the laser with the like a sandpaper, rotating sandpaper. It's a rotating diffuser, which will produce the quasi thermal light. And lo and behold, it works really nicely. So these images, for example, are done with the diffuser, where we have about 0.06 photons per pixel to record the image of like a small portion of the wing of some unidentified animals. My graduate students assured me that the animal was dead before he found it, because I did stop him for killing a couple of the moths around, because but if I trust him that no insect was actually harmed in these measurements. But we have this wing, and it's fairly small, so it's got 1 centimeters. And then if you put it in the setup, when we illuminate it with this with the pseudo thermal light, we actually can resolve it quite nicely. So you can see that even without any binning, we can still see the structure. If you bin just a little bit, we can see it even better. We were able to, using the true thermal light, we actually were able to reproduce these images even with the lower photon counts. And here I think the limitations is how well we can mode match our local oscillator and our thermal field. It was easier to do with the 4-wave mixing when we know exactly where the lights are going. With the thermal light scattered by the sandpaper, kind of slightly harder to do that. But you can see that actually with some binning, we can again reproduce the image quite nicely. And we can, of course, we ran our standard set of measurements, looking at the signal to noise. You may notice, if you have a photographic memory, you may notice that we're using much smaller sizes for the binning than for the light, and that's because the origin of improvement when the light is binned for quantum squeezing and for thermal light is a little different. In the quantum squeezing, we have to bin to match the mode of the squeezing. That's kind of put the limits. So if our mode is about 10 pixel radius, we basically have to reach this limit to get a signal. Whereas when we do the binning for the thermal light, it's mostly connected on how many photons we detect. And this brings me to basically the theory. I'll just put this slide to kind of impress you, and maybe just put in use that we don't just hand waving our equations. Our theorists did serious calculations of modeling the whole structure and how this method works. So they know that things are working. And okay, apparently I've kind of fall asleep on this slide a little bit yesterday. So if we calculate the signal to noise ratio, again, for the simple case when we have either unobstructed beam or some transmission, some absorbing limit with region with the transmission T, we can calculate the signal to noise ratio. This one is for the classical light. This one is for the thermal light. And we can compare our theory and experiment. And you see the matches quite well. In fact, you see there are multiple data points here, and that's because we run 2 parallel tests. In one case, we change the bin size in our image, so basically how many pixels we collect the information from. And again, we have this image here when half of it is light, half of it is dark. So we can measure everything we need from a single image. So we can change the bin size. That's, I think that's red and black points over here. But we also can actually just change the gain of the 4-wave mixing. That will also change how many average photons we have. And you can see that both of these methods give us exactly the same curve, and they're in a good I think in a decent match with what theory predicts. So we do believe that we can do this quantum shadow imaging even with the thermal light, which is not exactly quantum state. We can compare methods, of course. So theoretically speaking, squeezing is still better. So we should be, for the low average photon number, we expect that the signal to noise per like single image without extra averaging, squeezing will perform better for the really low photon number. If that's the main purpose, it's worth kind of investing in using the squeezing. However, thermal probe is not too much behind. And what is important, it's actually better than, for example, the regular intensity imaging with some dark noise. Here we have a 10. We have a fairly fancy camera. So this 10 photon counts per pixel is not too bad. And the other advantage of the thermal light, of course, is that we can basically create it for any wavelengths whenever we need. And do you have a few more minutes just to?
Go ahead.
Okay, so this is something is really a work in progress. So if you talk to me in a few weeks, I may pretend that I didn't say that because the next idea is to kind of look at possibility to avoid using camera at all. So if in our quantum shadow methods, we are trying to avoid using the really fancy camera with extremely low shot noise, dark noise, here we want to see, can we even kind of avoid using camera at all to get the shape of the light? And the idea is, of course, is the single pixel imaging, where we replace kind of selectivity, spatial selectivity of the camera with shaping of our fields. And sometimes it's just like light which is reflected, and then you just collect how much light is on the photo detector. In our case, of course, we're going to shape the local oscillator. So the experiment is the way it's run right now. It's similar to how it was for the previous squeezing experiment. When we create squeezing, we put the object into the squeezed vacuum part. But now what we do is we shape the local oscillator. We can overlap it with the different Hadamard modes. And then we just measure how much noise we detect for different phases of the local oscillator. If you still remember my equation from the homodyne detection, balanced homodyne detection, the intensity, the photocurrent was essentially proportional to overlap between the local oscillator and the quantum field. So now we add the spatial part for it. So we can basically look at the noise, look how it changes for the different modes, and try to make sense out of it. And again, this is mostly just a teaser with a huge asterisk that it's preliminary and may not necessarily work, but it looks like it's working. So now if we detect how much quantum noise we have, we can compare it with the classical introduction. Like if we actually feed some of the classical field and look at the interference between the local oscillator and the classical field, we can recreate, for example, this kind of two wires crossing here. If we look at the quantum noise, obviously it's not quite as good. We're still working on it, but you definitely can see some of the features here. And what is kind of exciting is that our previous methods, the quantum shadow imaging, was only sensitive to the absorption. However, this method might be also sensitive to the phases, because if you keep track of what quadrature of the noise you detect, so for example, here, in the experiment, there is actually overlap of layers of transparency. So we have no transparency here, one layer here, and another layer over here. Oh, one of those. So essentially the transmission is similar through all the layers except on the boundary, but the phases are different. And therefore, in these methods, we can actually kind of recreate these phases by keeping track of what quadrature of the noise we detect. Again, obviously the classical looks better right now than the quantum, but on the other hand, as I said, we're still working on it, and we're really the kind of the how we do it changes almost every day. Okay, so I think I'll conclude here. So hopefully I was able to convince you that we may have a new methods of using the noisy quantum fields like squeezed vacuum and maybe even the thermal state to detect the objects in the situation where we don't want to expose the light to a bright light. And maybe we can even extend these methods of to be able to predict the shapes of the objects even without actual camera. And I'll complete just saying thank you to my group at William and Mary. We have a lot of different projects. I told you about only one. If you're interested, please come to visit us or invite me again in the future. And this is just how our collaboration meeting goes with our LSU team. Of course, we were doing Zoom before it was fashionable. So, and this project was supported by the Forcer, which I have to tell you. All right, thank you.
Thanks a lot for this super interesting talk. It's actually very topical for me because I'm teaching quantum optics, and we talked about what you just talked about. So thanks for that and giving a bit of more insight. I'm sure there are a couple of questions. Dima already has his hand raised. What's your question, Dima?
Well, first of all, thank you, Irina. That is very interesting. That's a very interesting idea of using noise properties for imaging, but it got me thinking into, actually also, I was very happy to see when you said, can we use non-squeezed light? And I started thinking about it, and I started thinking about G2, the second order correlation function. But then I started asking myself, what about G1? So for instance, if you have like this corner, that's a nice simple shadow, right? And you actually use a laser, then suppose that you put, for example, an interference filter that's adjustable in front of it, and you start modulating it going, or put an interference filter and then modulate the laser or move the filter or something. So then the part that is blocked is just noise from the camera, so nothing will be modulated whatsoever. But but the part that is not blocked will be modulated, and this would be sort of G1 first order coherence imaging, right? In a way, will that give you enhancement of contrast as well?
So okay, so just make it. So the idea would be, let me see. Let me. Yeah,
this there was this corner.
Yeah, so just to make, yeah, so just to make sure. Yeah. Yeah, so this is a tradition. Yes. So what you mean here is to modulate the light coming in.
Okay, yeah, that's actually is even simpler. That's actually even simpler than what I was saying. I was thinking modulating the filter, so checking whether the light is coherent or not, just simply coherent in terms of monochromatic, but you are saying that actually don't even need that, just modulate, put a chopper, then the part that's blocked will not get modulated, the part outside will get modulated, and you can try to increase signal to noise ratio that way.
So I will need to think about it, because again, the main enemy for us is a dark noise, right? So if we start to modulate anything, it will still be on top of the large dark noise. And of course, it's kind of, I think the trade-off here would be is that in order to take advantage of kind of this phase sensitive detection now, because essentially you can maybe synchronize your camera.
Yeah, in fact, I think you can buy, I think we have downstairs in the lab something that's called a lock-in camera, actually, exactly for this purpose, right?
Right. So, but then the question is, would it increase the exposure of, like, how many photons interact with your object? So I think if we look at that, it might not give a overall advantage.
Okay, I also have to think about it. But it seems like with this method, you're like filtering because your noise, it doesn't know anything about the phase, right? It just always is there. It doesn't know about the coherence of the light. It doesn't know about its modulation. So there are many ways to pick out of the overall noise, only the part that sort of depends on your signal, right?
I think so. No, I get, again, is that the only way to to do that? No. I think what we try to do here is to amplify the useful signal by using the optical field, which does not have to interact with the object. So, and in this case, the thing which we amplifying is the noise. And the reason why we need to have a noisy quantum field is because the coherent field and the coherent vacuum, they have the same exact quantum noise. So we won't know which one is going through. If we have a noisy field, we can do that. Now, I will definitely not claim that there is no other ways to do the amplification. But at this point, I would say, okay, let's, if you suggest something, I would say, well, we need to take a piece of paper and start calculating what is signal to noise for the average number of photons, and kind of, is it like extend the exposure, for example.
Yeah. So I guess I suggest to you to at least look at the first, just the fact that the laser is very narrow spectrally, and the noise doesn't care, right? The noise will be everywhere, and yeah, so maybe there's a way to take advantage of this. But I see what you're saying.
Maybe, yeah. Okay, and I think there was one question in chat.
Yeah, that's by Oleg. Oleg, do you want to read it, or shall I read it, or we read it together? I can
Together would be very nice.
Together?
Yeah.
Okay,
let me read.
No, it's okay.
Okay, actually, it's a very, very simple, not simple, I mean, kind of stupid question. You use a lot of lasers, but your imaging actually just a like plain picture. What about holography? Probably it's possible to get some advantage in holography and stuff like this.
So maybe, again, I think most of the lasers we use here are for to like create the squeeze lights. So I think ultimately the optical setup is quite simple. The imaging part of the setup is quite simple. I think it's using the holography may be an interesting kind of development. I think what I talked, oops, let me scroll. What I talked here might be kind of a step in this direction, because as I said, in the previous measurements, the method was limited to measuring only the amount of absorption or transmission. So we wouldn't have any phase information. I think with this method, if we make it work, we may be able to recreate the phase information, and that's may enable the more like three-dimensional recreation of the shapes. But we really need to check that it's possible. But it's an interesting idea. I confess we haven't thought about this direction before.
Okay, I see. Thank you.
Are there other questions? Small little question, someone? A Christmas question? All right, I guess everybody's tired and extremely warm under their costumes. No, Ferdinand is unmuting himself. Do you have a question? No,
I just want to thank you, Arne, for doing this job fantastically this year. Once again, together with Mustafa, you're a great team. Thank you for this. Just taking this occasion to thank you both for doing this job for whole Quantum Group.
cool. How nice. Thank you. Well, and then I think if there are no further questions, that brings us to the end of this year's Quantum Seminar series. Thank you, Irina, for the super nice talk.
Thank you. It was my pleasure.
We hope to have you here at some stage, of course. I just don't know when that potentially could happen. I stopped making predictions about the future. I live in the moment, which is good. So yeah, have a great Christmas. Thanks again. Good transition into the next year, and see you all on the other side. Thank you.
Thank you so much. Thanks, Irina.